Yes, by that introduction, the expectations are always set pretty high. So I can probably only disappoint you. But I already got an applause for you without doing anything, so it should be good. How many of you would like me to present in English? Okay, bear with me for like 10 seconds or so. Obwohl ich ein bisschen Deutsch spreche, würde ich meinen Vortrag besser nicht auf Deutsch machen, weil mein Deutsch nicht so gut ist, dass ich hier eine Stunde reden kann, ohne dass Ihnen schon Lachen oder Schreien anfängt. Also für mich ist das, da kommt man manchmal schon das Lachen. Also für mich ist es einfacher im Englisch. So this is a story about a hobby project. So I do not build self-driving cars for a living. That probably wouldn't be a good idea. So what you typically see if somebody describes a project in a presentation, then they start with the introduction and then some what will be the agenda, and then we had this and then we did this, and then you're waiting for an hour and the tension builds up, and then you get a demo at the end. So I'm going to relieve you from all this tension right now and start with the demo. But I couldn't bring the car on the plane, because if you take a piece of electronics with batteries and lots of wires, airports tend not to like that you bring these things on planes. So it's still safe and sound in the Netherlands. But let me start with a recording from a presentation that a colleague of mine did before. Start with the accelerating demo right away. And I must say that this is the scariest demo I've ever done, because typically when I demo stuff, my hands are on the keyboard and I can control what's going on. And in this case, I can't touch the keyboard because the car should drive itself, right? So we have the car up front here. What you're seeing on screen is our web interface where we can control it. We'll talk all about this later. And the objective now is that the car I will start the car. It should drive itself, stay between the white lines, and then stop when it's not seeing any lines anymore.
So if everyone will cross their fingers now, right? See if it works.
If you're up front, I would advise you to lift up your legs, because we have we have an idea what's going to happen, but unexpected things happen all the time. So let's see, we're connected. Here we go. we were sweating it a little. We were sweating it a little, indeed, because we had practiced, basically like trained the car in our office with a nice, clean, gray floor, and then we would tape white lines on there, and the objective was that the car would stay between the lines. And then we got to the Devox Antwerp venue, and we were prepared for a talk and taping the white lines on the floor and set the car, and it didn't see anything. It saw a lot, because there were all these little white dots on the floor. So it actually was seeing like thousands of small little lines. And there were like 800 people in the room seeing us do the demo. So we had 5 minutes to fix it. So we had to tweak the algorithms and brightness a bit. And well, it worked kinda, but this was once and for all for us a big indication that lighting conditions are extremely important if you control a car only based on a camera image. So my name is Bert Schrijver. I've already had an introduction, which was great. I work at OpenValue, a Java full-stack consultancy company. I typically do this talk together with my former colleague Tim, but as you can see, Tim is not among us today. He couldn't make it, but he's done lots of work too, so credit to Tim as well. So how did this all start? Do Tim and I build self-driving cars for a living? No, this started as a kind of as a hobby project. So we wanted to do something nice and challenge ourselves in doing something different from the typical serious enterprise development stuff we were doing in our day-to-day job. So we set ourselves a challenge to build a small self-driving car. So we got 4 teams to work on this, and the rules were fairly simple. Each team gets a basic RC car kit, so a small remote-controlled car, a limited budget for adding sensors and electronics to the car, and then we would do 3 races. So the first one was a drag race, where the car needed to look at a start light. If the light goes off, the car starts driving. It should drive 50 meters between 2 white lines and then stop in a stopping zone. The second race would also include corners. And the third race would include multiple cars on the track. So we never made it to the third, but we did the first 2. So what did we start out with? A basic RC car kit. So what does a car have? It has wheels, you can steer it, it has an engine, and there's a battery in there. Basically something that you can buy for maybe around 50 euros in total if you add batteries and servos, around 100 euros. Then we need to control it. So typically, the car has a steering servo and a speed controller, and you link it to a wireless receiver, and the wireless receiver receives wireless signal from the controller with 2 sticks where you control it. So we took out the wireless receiver and put a Raspberry Pi on the car. So why a Raspberry Pi? Because every project gets cooler if you throw in a couple of Raspberry Pis, right? So there was an obvious choice to make. It needed to get power, so we bought this thing in China that converts the 7.2 volts from the battery to the 5 volts for the Pi, so we could hook it up. And then we had a Raspberry Pi on there and a wireless network stick to be able to connect to it. Then we needed to decide on which software to run on it, and we chose to use Vertex. How many of you have heard of Vertex before? Ooh, just a couple. So Vertex is a toolkit for building reactive applications on the JVM. So it's event-driven and non-blocking, so it really allows you to make real high-performance applications, and it's really general purpose. So we used it at a previous assignment where we were building highly concurrent educational applications that were running in the AWS cloud, but you can also use it to build self-driving cars. So we chose it because it's very lightweight, both in terms of disk size, memory usage, and CPU usage. It's really fast, and it's polyglot, so you can write Vertex modules with everything that runs on a JVM, with JavaScript, with Ruby, maybe even PHP, I'm not sure. And the most important thing is there's a distributed event bus. So if you build a Vertex system, you can build it consisting of multiple modules that you can run in different places, and they automatically cluster together. And you can send messages seamlessly using this cluster to the different parts of your system. So this allowed us to run some parts on the Pi and some parts on on a computer, and then move parts back and forth without really having to do too much on our infrastructure. You can even extend this event bus to the browser so that we can send messages directly from a web browser over the network to some stuff running on the Pi. So if you'd like to know more about Vertex, I did a talk about Vertex once. You can look it up on YouTube. So then we need to connect stuff. So we have the steering servo, which is buried somewhere below here. We have a speed controller, which is somewhere here. So a speed controller controls speed, surprisingly. But what it does is if you would hook up the engine directly to the battery, it would only go full speed ahead all the time. And you want some control of this. So a speed controller regulates the voltage that's going from the battery to the engine. It can also reverse, so you can go in reverse. So what we did was hook up the pins from the servo and the speed controller to the GPIO ports from the Raspberry Pi. So GPIO stands for General Purpose Input-Output. And you can connect lots of interesting stuff to a Pi with this. So there are 3 types of pins, 5 volts, 3 volts, and ground, and data pins. So that's 3. So what we did was hook up the servo to these data pins, and then we would need to find out, okay, what signal do we need to send to servos? So it turns out that there's a standard for this, and the standard is called PWM. Pulse width modulation. So what you're doing is you're sending pulses, so like just small currents over the wires of variable width, and then the servo and the speed controller can interpret this, and you can control it. So there's an open source utility called Servo Blaster. If you install it on a Pi, then you get a Linux interface, dev Servo Blaster, and you can basically send commands there. So you could do echo 3, let's say echo 200 greater than 3. No, echo 3 is 200 greater than dev Servo Blaster. Then you would send you would set servo number 3 to value 300 in device dev Servo Blaster, and this would do something. Maybe set the servo in a certain angle, or maybe set a certain speed in a speed controller. So our first prototype was exactly what I've told you now. We have the Pi, it's connected over Wi-Fi to a Mac. We're SSHing into the Pi and typing commands and echoing them to dev Servo Blaster. So set the car straight, echo 3 is 200, dev Servo Blaster, enter. Car starts blasting away at full speed. Echo 3 is 0 dev, and it was out of range and it crashed into the wall at the other side of our office. So at that point, we realized that safety was important, mainly to preserve our car. So what we did was we were now switching to running Java on there and Java on a Mac. So we implemented a heartbeat that every 100 milliseconds there would be a heartbeat between the Mac and between the Pi. And if it would not receive 2 or 3 of these heartbeats, it would kill the engine to make sure that it wouldn't keep driving when we were out of range. And we installed a LED on there that we could see that it was connected. Then we needed to get eyes on there, because with a budget of only 150 euros, you're not going to get radars or ultrasonic sensors on your car. Maybe ultrasonic sensors, but we chose to go for a camera. So you can pick up a Raspberry Pi camera for about 30 euros, click it into the Pi, and then you have a, I think, 720p video feed. So how do we get the video feed? There is the Raspberry Pi Cam web interface, which surprisingly is a web interface for the Raspberry Pi camera. So you can just install it on the Pi and run it, and then you can configure video settings using a web interface. So you can set frame rate, resolution, brightness, contrast, and you can stream video from there. So I think we got an MPEG-4 stream and stream it back to the laptop. So now we are about ready for the road. We're ready to do some manual driving. So what does it look like? We have a web interface. Here we see events from the Vertex event bus, mainly health checking events. Here's a small legend of how you control it. So left, left, right, right, and then some things like B is stop, space is emergency, C is center. As you can see, we put a lot of thought in the UX of our application. And here you see the vision of the car. So if you look at the previous slide, we have this fisheye lens installed on the camera. So it's a fisheye lens meant for smartphones. You click on your smartphone. We installed on the camera to get a wider field of view, to see lines closer to the car. So this is the view the car was seeing. We noticed that the higher up we would put the camera, the better view of the road we would have. So the things you see on the right, skip them for now because this is part of the autonomous driving, but this is what the car would see. And then we could use our Mac and a web interface to drive, control the car, and see what the car was seeing. So now we basically had a normal remote driving car with a 3,000 euro controller, and nothing special yet. So it's time to make it a bit more special. So we wanted to learn how to drive, and we wanted to use computer vision to do this. So we were looking around for options on how to do computer vision in Java, and we learned that OpenCV is the most widely used library. So how many of you are familiar with OpenCV? Oh, quite a lot. More than Vertex. Nice. It is one of the de facto machine learning libraries and libraries for computer vision. It is implemented in C++, and it can run on your GPU. And the nice thing is there are Java bindings for this. So you need to compile like native binaries for your machine. But then you can use Java interfaces to directly control this C code from Java. And there are many resources and tutorials available, so it was fairly easy for us to get started with OpenCV. So this is basically our image pipeline. So there's a couple of steps we chain together to go from the raw camera feed to having some idea of where are we on the road and in which direction are we. So you start with taking the raw image and applying edge detection. So edge detection is a way of detecting edges in an image. And what we're using was the Kenny algorithm. And the Kenny algorithm has been around for ages, and it still works fairly well. So if you take the raw image, you can see there's nicely detecting some lines here, which are actually the white lines on the road, and some other lines in the back, which I think is a chair, maybe some reflection and some other things. So then we needed to go from edges to lines. So we used a line transform algorithm that can detect lines based on edges. And when we were looking through the OpenCV documentation, there were two options. There's the U-line transform, and there was the probabilistic U-line transform. And we read somewhere that the probabilistic one performed better, so we decided to go for that one. As you see, proper engineering and design choices here, which is fine for a hobby project. So then we needed to turn these into lines. So what you're seeing on the first image is actual output from the Kenny edge detection. The second image is the raw camera image where we have already plotted these lines on there. So now we have these lines in a matrix that we can overlay on the image, but it's not like raw image data. These are already like vectors we're drawing ourselves. So then we need to, you see that the lines are kind of stopping on top here, and they're being interrupted. There's even a small horizontal line on top. So then we needed to make some more continuous lines of this. So then we filter these lines and group them and make the left edge and the right edge of the white tape into one line. And then you can see that we can plot them all the way through to the horizon. Because you're pretty sure that if this line it goes all the way to here, then the last part probably will continue the line there. You're just extrapolating. So once we have the left line and the right line, we can now determine the center of the lane. And then we now know where are we compared to the center of the lane, and what is our angle with the center lane, the left line, and the right line. And this was our initial steering algorithm. Look what we are, how we are positioned against these lines, and then steer based on the angle that we are. So if we're positioned like 30 degrees to the left, maybe steer 15 degrees to the right. So how does this work? Well, actually, it's fairly simple using the OpenCV bindings in Java. So we have a class here called image lane detector, and this has two subclasses we're using. One is the edge detector, and one is the lines detector. So if we dive into the edge detector, there are some configuration, like some thresholds you're setting. But actually, the only line that really matters is this call. So we're saying imageproc.kenny. And this is calling via the Java bindings the native C code that is performing the Kenny edge detection on this image. And it's about the same for the lines detector. There's also some configurations like what is the threshold for something being a line, what's the minimum length and the maximum length of the gap between the lines. But also here it's still a one line call. So we're saying imageproc.uLinesP. And this will fire up OpenCV to do the lines detection for us. So we then decided we needed an architecture because the project was maturing and we didn't have an architecture yet, and every project needs a good architecture. So we decided to do this. And is this a good architecture? The most accessed file in our repository is the README file, where we are describing which component does what. So it can be confusing from time to time. But the idea we had was, our team was called, I'm not going to say how our team was called, because I'm going to let you guess. Does anyone recognize these characters on the screen here, the names?
Cowboy series.
Yeah, you're right. Yeah, Cowboy series with a big orange car. It's a while ago.
Blue and green.
Yeah. Oh, you don't know the show here? It's the Dukes of Hazzard. It's like a show from, I don't know, 20 years ago or something, where two farm boys have this fast car that's continuously getting into trouble and the police is chasing them. So we named the components of our system after characters of the Dukes of Hazzard. So with the image feed coming from the camera, this is processed by Daisy. Daisy is a friend of these guys, and she's always keeping an eye on everyone. And Daisy sends the intermediate images to Roscoe. So Roscoe is one of the officers there. So this was basically our debugging output to see which lines have we detected and how can we plot these on the images the camera is seeing. So Daisy processes the image feed and she sends the angle and the distance of the car to Luke. And Luke was kind of like the leader of the group. So he's sending instructions on how to steer and how to increase or decrease the speed to Bo. Bo was always the one driving the car. And Bo is sending commands to Servo Blaster, which the steering, which the speed, and can also shut off the car in case of trouble. So then we have Boss Hawk, which was, I think, the chief of the police. So this is the control interface, and this both sends manual inputs to the steering part, because we will also override like manual inputs, and also it checks the heartbeat, and if the heartbeat fails, it shuts off the car. So everything on the right is running on the car. So this is mainly only the heartbeat part and the main control module that's accepting instructions. And then the rest, the image processing and the safeguards and the debugging interface are all running on a laptop. So we chose to do this for two reasons. The image processing can be fairly heavy, and the Raspberry Pi had trouble processing all these images. But also it was easier for us in terms of deployment cycles and feedback times, because we could now just stop the application on the Mac, restart it, and continue there. Otherwise, we still needed to package it, deploy it on the Pi, and start it there. So we now have a car that we can control. There's an image feed, we have processing, and this should all be perfect, right? We're expecting it to be behaving at least as well as a self-driving Tesla. Well, in reality, it was more like this. It was okay, you know, it could drive itself. It would fail every now and then, and it was still fairly like hacky, everything. So this is one of our first videos we have, and this is one of our big breakthroughs, because here we have the first like integration test. So the car is looking at this light here. When the light shuts off, it should start driving, stay between the lines, and then stop in a stopping zone, which is below here.
All right.
So here we are, 3 grown men in the kitchen, getting all excited over a little car that's driving 2 meters. But this was a breakthrough for us, right? And then this is a video of a bit longer practice run in the hall in our office. So it's doing okay, but if you maybe you saw the car starting to swerve a little up to the end. And one of the attendees at one of the early editions of this talk called this autonomous drunk driving, which I could agree with. But what we were seeing was that because we were purely steering based on the angle the car was making with the road, you're in this angle, you need to correct, and then you tend to overcorrect a little. So the longer we were driving, the more it was swerving. And Tim had been telling me all the time, do not look at the angle, do not look where you are, but look where you need to go. Try to look at the horizon. And I was saying, yeah, I'm going to do that, but I didn't do it, and that's why it was swerving so much. So then we were practicing in the office, and our office is in next to a big hall where regularly events are organized. It's like two football fields in size. And in this case, we were practicing, and there was I think a baby expo where you could, buy baby strollers and baby rooms and everything regarding babies. And we were practicing here, and there's like this little passway here. And while we were practicing, the car drove through the passway. It made like a 90-degree turn and drove to the passway. And people were screaming there, "Ah, it's a drone!" And we were running after the car to grab it there, because for some reason the safety mechanism didn't work too well. So then we were kind of figuring out what happened here. And then we came to the conclusion that probably it kind of got lost, and it was making a turn left, so it continued to turn left. And then it thought, oh wow, here are 2 nice white lines to go through, and that would probably be the road that I'm looking for. And then here's another video where we are kind of practicing in the office with a bit of different lighting conditions. And there's some reflection on the floor, which make it a bit harder to detect the lines. And the car is stopping at the most important place of the office, the bar, obviously. So did it went this well all the time? No, this was about the 10th take of this video. But hey, that's marketing, right? But I have a video from one of our less successful attempts, from 1 minute before the other video. And then we had no idea what happened here, until somebody from the audience said, "But yeah, the car is doing pretty good. It's right between 2 white lines." And I'm like, "What do you mean? It's next to the 2 white lines." And he said, "No, 1 line is here, 1 line is here." So probably it had picked up the reflection from the line and thought, well, it's a good idea to steer here. So then it was time to race, the first race, the drag race. So there were 4 teams competing. 1 team, the car didn't move at all. 1 team was built by a group of front-end developers, and I didn't even tell the outcome yet. You're laughing. The car looked awesome. It looked great. It had lights on there, and it was really fast and flashy, but it didn't drive by itself. So, but the guys were smart. They actually had quite a good idea to like set the car to a certain speed, and then like measure how many seconds it would take to get to the stopping zone, and then after those seconds automatically shut off. But unfortunately, they didn't really make it. So there were 2 cars left. Our car, we were practicing the entire day, and there was another team. The other team, actually, the steering algorithm was a bit better. So they were better in staying in the lane, swerving less. So during practice, I thought, okay, well, I think we're going to end up in the second place. So then, for some brilliant reason, we had decided to practice during the day and do the race at night. And I'm not sure how it is in Munich, but in the Netherlands, it gets pretty dark at night. So as you can see, the hole was dark. So we got some lights in there and some cars to light it up. And obviously, this brings extremely difficult lighting conditions because it was light, dark, reflection. It wasn't going to work at all. So in the final race, the 2 best cars raced head-to-head. And we started racing. And about halfway, the other car that was going faster, they switched lanes in front of us and then continued in the lane and stopped in our stopping zone. And like right after the car switched lanes, our car went off to a 90-degree turn and went off like into the darkness. But, there's a but. The rules clearly stated that if any car would leave the lane, then the place where it had left its lane would count as a distance. And although the other car had reached the stopping zone, it had reached the wrong stopping zone, and it had switched lanes like 5 centimeters before our car left the lane. So we won, yes. But I have to admit the other car was better. And it was mainly because of their steering algorithm that was better. Because apart from this, they were also using OpenCV, and it was pretty much the same solution as ours. So then we continued, and after all these months, Tim had been saying to me, like, you need to not look at where you are, where you need to go. So, okay, finally. So what we did is looked at like the horizon where the 2 lines from the side of the road would cross, and then pick the middle of this point, and then make the car always steer towards the middle of this point. Kind of steer like whether you need to go to your point on the horizon. And this also made it easier to kind of navigate through like curved lanes. So here's the first video from this. The ping pong ball is just there for reference. So you see it's actually steering to the middle of the road in the end. So the first time we tried this new steering algorithm, we tried it on like a exactly the right lane, and the car just drove straight ahead to the end of the road. I'm like, oh crap, something is wrong. So then I put it on the side and started again and still drove to the end of the road. So looking at the horizon looked a lot better than just looking at the angle. And then we kind of wanted to go one step further and see if you could navigate through corners. So what we did was make the lines that we were detecting a bit shorter. So we shortened the field of view from our camera. So you can see that the Kenny image is now a lot smaller. And the lines that we're plotting, they are starting like 30% from the bottom of the image and ending like 20% from the top of the image. So these lines are now sliding over the image feed we're seeing. And that worked out pretty well. It's going slower now because the battery was almost dead. So that was pretty good, right? We were excited about this. Although I must admit that in our first tries, the car didn't really make every corner and it didn't really see every line too well. So what we did was, not here. The corner to the right, we changed the lines a little so it could make it. If you look to the right here, the tape is exactly aligned with the shadow of the pool table. That is not a coincidence. So we kind of bended the rules a little, but in the end, our car was the only car that could navigate this track, so we won that, which was nice. So, given this knowledge, how does our solution compare to self-driving cars in the real world? If you look at Waymo by Google and Tesla. Well, let's first look at the different types of autonomous driving vehicles. So you have level 0, basically a car that can do nothing autonomous. Level 1, you can do one thing, maybe cruise control or automatic braking. Level 2, you have at least 2 functions. So if you have adaptive cruise control and lane assist, this is already some sort of autonomous capability. Level 3, there are dynamic driving tasks that the car can handle by itself, but they might still need intervention. Level 4, a car is officially driverless in certain environments, so based on geographic location, for example. And level 5, completely entirely autonomous without any presence of drivers. So I think Tesla is about at level 3. They want to believe they're at level 4, but I would say they're at level 3, because if you're using autopilot at the moment, you still need to hold the steering wheel or put 2 oranges in the steering wheel. But I don't think that this helps in your reliability. So if you look at self-driving cars built by Waymo, there are basically 2 approaches. One is using expensive hardware and one is using cheap hardware. So Waymo is using expensive hardware, mainly a LiDAR on top. So a LiDAR is a razor LiDAR. I'm not sure what I said there, but I meant a laser radar. And it sends out like thousands of laser pulses per second, receives them, and then kind of plots like a laser 3D image of the world around it. And these things are fairly expensive. They used to be around 100k euros, maybe now 50k or 30k, but still quite a lot compared to the cost of a regular car. There are some supplemental sensors like ultrasonic and radar and stuff like that, but the LiDAR is the most important thing. So how does a LiDAR system see the world? Could be something like this. So it's continuously sending out laser pulses, and it knows what the distance is of each pulse, and this helps is like plotting a 3D world around you. And the good thing with LiDAR is that it's not susceptible to lighting conditions or clouds or rain maybe, but it works a lot better than cameras because it basically shoots through everything. And there are already companies, I think like TomTom, that are building these LiDAR maps from the world. So there are already some pre-mapped environments that you can buy where you have a complete 3D map of the environment. And typically this is used as fallback to like check the environment that the car detects by itself. And then there's the approach by Tesla, which is mainly using cheap hardware like cameras, a radar, and ultrasonic sensors. So it's quite impressive if you see what Tesla is doing with only cameras, regarding the fact that we found that computer vision is so dependent on having a clear vision of the road. Obviously, Tesla is using machine learning to train their system. And the nice thing about Tesla is they have been training their system with thousands of drivers for years already, because every Tesla driver is manually driving his or her car and sending sensor data back to feed the model that Tesla is using for their autopilot. So I think it's safe to say that Tesla has the best trained neural network for autonomous driving of every company in the world, because they have millions of miles in there already. So this could be maybe what a system in a Tesla could see based on cameras, object detection and stuff like that. But as I hear up front, is this a Tesla? That's a strange T. No, it's a Honda. So this is a car from George Hotz. And George Hotz became famous years ago for being one of the first to jailbreak the iPhone, being one of the first to hack the PlayStation. He's like a interesting person and a good hacker. So he found out that he could use I think a Bluetooth ODB plug to connect to his Honda and then control the lane assist and adaptive cruise control. So he took his phone and he started hacking, and he made a self-driving system by himself. So the phone has a camera, it processes the images, it sends commands to the car and then steers it. And then Hotz invited a journalist, like, come see, I built my own self-driving car. Journalist gets in the car, they sit, Hotz leans back and let the car do its work. They go back to the garage. He says, so what do you think? Yeah, it was amazing. Yeah, it was the first test drive. So then the journalist makes an article, and then I think it was in the US, and the US government didn't really think it was a good idea that a single person was making a self-driving car. So they said, you cannot make a self-driving car as a person. But George Hotz is not stupid. So what he did is said, okay, I'll start a company that makes self-driving cars. So you can actually now buy this stuff. Most of it is open source. I think only like the image processing pipeline is proprietary. You need to pay for it, but it is available, and it's a nice like open source approach to this. Although I would rather trust like the thousands of engineers at Tesla than one single smart hacker. So safety, as I said before, is important. So what can you do with self-driving cars is limit them to a certain geographic location. For example, some cars are only allowed to drive in Arizona because the weather is always nice, the roads are good, and there's always clear view. You can let the car drive under strictly defined conditions, like only when it's sunny and not when it's raining or snowing. Redundancy, just like in a plane, make sure that you have multiple systems that can correct each other and like detect errors. So if you had like 8 sensors, one of them has a failure, then the other 7 can basically say, okay, you're stupid, just listen to us. And that's the same thing with using multiple sensors. It's also important to isolate control systems because I've heard from some of the guys from Computest, like a Dutch IT company, they were able to get access to the driving system of I think a Volkswagen by first connecting over Wi-Fi to the infotainment system and then through a few hops in the car being remotely I think able to lock and unlock the car or something. So that was quite scary. And obviously a human intervention fallback is like the best legal way of handling self-driving cars at the moment. And if you're using only computer vision for AI, there are also weaknesses. So this is a research video from 2 guys who are using one of the most widely used object detection algorithms that's really good at detecting people and chairs and stuff like that. But one of these guys has a strange like printed patch on his belly with, I don't know, maybe some umbrellas and bikes, I'm not sure. But the guy on the left is a person. Look, I'm a person, I'm here. Hey, but wait, I'm a person too. Why are you not detecting me? I'm a person. So because of this patch, the computer vision is confused and does not know that this is a person. It knows this is a chair. The other one is a person. But even if this guy is, look, I have this, but I'm just a person. Hello? And then he takes it off and he immediately becomes a person again. Look, he's a person at all. So imagine that you are crossing the street, and you've just bought a toy, I don't know, for your kid. You're holding it here, and the Tesla thinks that you're not a person. That could be strange, right? So let's move to ethics a little, because ethics are really interesting and also a bit scary. So this story is about that. AI is really good in making split-second decisions about what to do. And the robot says like, okay, there are billions of people on the earth, but only a couple of self-driving cars, so I should always preserve self-driving cars because they're also so little. So let's move to a bit more serious things. There can be situations where an accident is unavoidable. So let's say that there's a car and the brakes are gone and there's concrete barriers on both sides, and the car is driving at full speed against 3 dogs crossing the road and 3 cats crossing the road. So the only thing the car can do is either continue driving and kill the dogs, or swerve to the left and kill the cats. So this is an experiment from the Moral Machine by MIT, where they are investigating like different morality issues to see like what would the human population choose and how can we apply this to like autonomous systems. So by a show of hands, how many of you would save the dogs in this case? Okay. How many of you would save the cats? Yeah, that's usually about 50-50. Think of the damage that a dog would do to your grill. But let's take it a bit more serious now, because you know with dogs and cats it's maybe sort of funny. But what if we have the same problem but for people? So you're driving your car. The brakes are broken. There are concrete barriers on both sides of the roads, and there's a family crossing the road in front of you. And on the other side of the road, there's a concrete barrier too. So you now have 2 options. The first option is to continue driving and kill the family that's crossing the road. The second option is to swerve and smash into the concrete barrier, killing the family, your own family in your car. So how many of you would take evasive action, slam the car into the concrete barrier, killing your family in the car? Okay. How many of you would continue driving, save your family, and kill the people on the road? It's a hard question, right? It's an impossible question. But self-driving cars will need to make these decisions too. So how many of you would be willing to buy a self-driving car that is programmed or that has learned to sacrifice your family inside the car? How many of you would buy a car like this? Nobody? Okay. How many of you would buy a self-driving car that is programmed or has learned to save your family but kill people crossing the road? It's still an impossible choice. But luckily there are organizations and governments thinking about this, like how should we handle this. And one of the rules that's fairly obvious is whatever happens, the preserving human life is always the most important thing. Preserving human life is more important than preserving material stuff or preserving like animal life. We should always try to preserve humans, which makes sense. Then the second one, when there's an unavoidable accident, you cannot make any distinction based on personal feature. So your age, your gender, whether you're sick or healthy, whether you're mentally okay or not. And this can already be debatable. So let's say that you have an unavoidable accident and you can choose between running over 3 little kids or running over 3 grandmas, for example. Do the kids have more right to be safe because they have their lives in front of them? I don't know. And that may be a choice that maybe you can make. But what if there's 4 grandmas and 2 kids? You know, and can you like exchange them against each other? These are still impossible choices to make, but cars will need to make these choices. Another thing that's good to know is if you look at the emission scandal that happened with a German car manufacturer. So this car was programmed to behave differently in emission tests to get a better score. The developers that built this, their manager told them to build this, they can go to jail for this. So remember that you as a developer, you can go to jail for doing something unethical that your boss tells you to do. So keep this in mind whenever you're building software. So back at the hobby side of things. Stuff that we like to work on is improve how we detect and navigate through curved lanes, maybe do line detection on curves, maybe use a sliding window to optimize our detection algorithm. One thing that could usually help is automatically recalibrate video parameters. So brightness, contrast, stuff like that. If you see that we're not detecting lines, try fiddling with the video parameters to see if you now are detecting lines. And the same for the parameters for Kenny and for the U line transform. Currently our debugging mechanism is looking at the UI while the car drives and trying to figure out what is going wrong. So it would be better if we would send like some metrics on we detected this line and therefore took this steering action. It would also be better if we would control the servos directly from Java. So now currently Java is executing a shell command and that's echoing to Server Blaster, which is kind of hacky but works. But I think that the two next big steps are first to move to, for example, a neural network that we can train by feeding the camera feed and the detected lines and our manual steering input into a network and then drive 10 million laps to our office and then have a trained network that may perform better than the rule system we have now. The problem here obviously is driving 10 million laps can take a lot of time. But you can use simulations maybe also to train this. And we could and should optimize for running everything on the car because currently most of the stuff is offloaded to a Mac, which is easy but could be cooler if the car will be all autonomous. The time is almost up. Do we have time for questions?
Sure.
Yeah, I was wondering.
Yeah, it's on.
Okay, cool. I was wondering, have you? I mean, it's mentioned in the what to do, like do video calibrations. Have you thought about more image processing before running your detection algorithms? I mean, there is an immense ton of stuff you could do, but it's also probably since you have time restrictions, you can't do that much, but there is a lot of filtering
Yeah.
you could apply that might really like change your images to be easier to interpret.
Yeah,
The Kenny is good, but I've also seen the weaknesses with with the carpet. That was a good example, I think.
Yeah, you're absolutely right. We can also do more like software steps to improve the image detection. I think also one big step we can take is by giving our algorithm a memory. So currently we are processing every image individually. So even if though it has set 10 images where it was driving straight, and then there's one image where it doesn't recognize the lines anymore, it's like, oh look, I'm not seeing lines. So that would also help.
Thank you for the very nice talk. I was wondering how many images you manage to process per second.
I think we're about maybe 5 to 10 images per second. It's mainly limited by the bandwidth we have from streaming the video feed to the car. So one big improvement could be to do the image detection on the car itself. One thing we might be looking into is using a stick that has hardware to do this. So for example, Intel has the Movidius neural compute stick. You can plug in your Pi and then run a neural network on there. So that would greatly improve the number of images. So currently we're limited to driving not so fast because we're not processing that many images per second.
Thank you very much for the interesting talk. I'm wondering what kind of latency you have there, how the time range from like recording the images to steering to the horizon.
Yeah, it's an interesting question. So how long does it take for a frame to be sent from the camera to the laptop and then processed and back into a steering command? I have no numbers on this, but my guess would be a few hundred milliseconds. So definitely not a second. Definitely not a millisecond, but maybe 200-300 milliseconds, I think.
Yeah, also from me, thank you very much for this very interesting talk. You mentioned adversarial machine learning, that you can manipulate image detection that does not detect humans, for example. You could do the same procedure when driving on the street and holding an image and simulating there's family in front of you, so you have to brake or smash the car in a wall, because else you're just killing the family in the street. So in advance, you could just hold the car, give the car some pictures to kill the passengers in the car.
Yeah.
So I think there's not a discussion if you kill the outside people that are not in the car, or if you kill the people in the car, because there is much more manipulation possible in killing the passengers.
Yeah, you're right. So one thing you could do to trick a car behind you is to have a big display on the back of your car that's displaying an empty road ahead, for example. But that wouldn't really make sense because then the car will run into you. But yeah, I agree that the weakness of purely vision-based systems is that they are fairly easy to trick.
Okay, so I have one question concerning the speed. Were you always trying to go full speed, or did you, if you detected a corner, slow the car down?
Yeah, that's a good question. So the speed is set to a certain specific value. So whenever we start, we start to drive at a certain speed, and when we see the stopping zone, we stop. The speed is set to the lowest speed that is comfortable with waiting on the car. And I must admit that initially we had a battery with a bit higher voltage where the car would go pretty fast, and we even bought a battery with lower capacity so that the car could drive slower, because the slower it gets, the more time you have to process everything.
And another question, have you considered using ROS for the car, and why didn't you choose it?
Yeah, I get that question a lot. I think it would be a good option. We decided to try to do most of the things ourselves to kind of get an idea of how does image processing work and how can we feed it into a car. But yeah, using some already well-developed open source solution could obviously have a lot better results than the stuff that we've done.
And another thing, ROS 1 up until recently was not that easy to run on the Raspberry Pi, which made it was kind of messy. So
you get a lot of benefits.
Yeah.
So any more question, or is it more lunch time?
All
now?
the code is on GitHub. I wouldn't advise you per se to look at it because it's a bit hacky, but maybe it could be good to have a laugh every now and then. I will post the slides on my Twitter account, twitter.com/@bjschrijver. If you have any questions afterwards, feel free to reach out on Twitter. I'm happy to help. So thanks a lot for your time. Enjoy your day and enjoy your lunch.